A couple announcements. First of all, tomorrow is the last day to withdraw, so if you feel like you're in a situation where you are concerned about your status in this course, please see me. Also, we will be needing our calculators in here for the next class. So next Tuesday, we need the calculators. We've been away from them here for about a month, but we do need them back because we will be wrapping up our stuff for this next exam with a bunch of calculation stuff. As a reminder, there are a couple of extra credit opportunities. We've talked about these already. Any questions on these opportunities? Okay, 29th is when? Next Tuesday. And that's actually the next time we're meeting. We will not be meeting on Thursday, Thanksgiving Day. So the next time we meet, this is due. This is going to take 3 days. If you wait until Monday night, you will not be able to complete this. So if you are interested in some extra credit, these are the opportunities. So any questions on anything that we have here to get us going? All right, next up, we are in Chapter 13. And with Chapter 13, you should be familiar with these terms. And we're going to kind of go through these here today to kind of kick things off. So when we start talking about solutions, we are all speaking the same language. And that does take us to that first Socrative app question that we have here. And that is, another name for a homogeneous mixture is, so get your answers locked in. Get your answers locked in. And for those of you that would like to take a look at this list here, again, these are the solution terms that we will be using throughout actually the rest of the semester, not here just for Chapter 13, but for the rest of the semester. They are solute, solvent, solution, soluble, insoluble, miscible, immiscible, gaseous solution, liquid solution, solid solution, aqueous solution, non-aqueous solution, dilute solution, concentrated solution, unsaturated solution, saturated solution, supersaturated solution, and solubility. So, and these are the terms that we'll be looking at today. And you have the question waiting for you on the Socrative app. We're going to take a look at that here right now. So we'll count down 5, 4, 3, 2, 1, and it is called a solution. And a solution is a mixture that we say is homogeneous. And by saying that a mixture is homogeneous, that means when we look at it, for example, these here are some solutions. By looking at these, you can't tell that there's more than one substance in them, no matter how close you examine them. If you were to grab them, you cannot tell that these are made up of more than one substance. So by homogeneous, that means when we look at it, it might appear as if it's only one substance, but it's really a mixture of several different ones, and we call that a solution. All right, then, brings us to the next term here. And again, we are going through a list of terms here today, solute, solvent, solution, etc. So your next question on the Socrative app is, in a solution, the stuff that gets dissolved is called, you can always ask the neighbor what he or she thinks. And we will count down 5, 4, 3, 2, 1. Wow. All right, it is the solute. So I guess we don't know that stuff. So come back here. Let's start writing down some definitions for these. These as a class. The stuff that gets dissolved is the solute. which means that the dissolving agent is called the solvent. So the stuff that gets dissolved is the solute, the dissolving agent, and that is the stuff that the solute gets dissolved into is called a solvent. And it might be helpful to know that water is often called the universal solvent. Water is often called the universal solvent because it dissolves many, many, many things. So if you're having trouble keeping solvents and solutes straight, think of water. Again, water is considered to be the universal solvent. Any questions on those? Okay, then the next terms that are up here. We've actually used the words soluble and insoluble before. Let's see what you remember. We talked about this when we were dealing with chemical reactions and precipitates. We say that if a substance is able to dissolve in a solvent, it is said to be what? So we'll get our answers locked in. 5, 4, 3, 2, 1. All right, very good. It's soluble. So at least give yourselves a pat on the back for that one. Next up, we've got miscible and immiscible. Anybody know what these mean? Miscible and immiscible. What do they sound like? If it's miscible. Yes?
Easy to not notice, as far as I know.
Easy to not notice?
Because you can miss it.
No, no. Nice try though. Has to do with things being able to dissolve in each other. And they pertain to fluids. They pertain to fluids. When we talk about fluids, we're talking about liquids and gases. And if we say that two fluids are miscible with each other, that means we can mix them together in any proportion. So if two fluids are miscible with each other, that means we can mix them together in any proportion. And if they are immiscible, that means we cannot mix them together. So let's see what you can do with these three fluids. You need to pick out two of them. So again, which two liquids are miscible in each other? In other words, which ones can we mix together in any proportion? We'll count down. 5, 4, 3, 2, 1. All right. Exactly. Alcohol and water. And of course, none of you are old enough to do that, right? Maybe not many of them, but again, that's what many of us do on Friday nights. Right? Mix together alcohol and water. And if we were to look at the next one, which two liquids are immiscible with each other? Count down. 5, 4, 3, 2, 1. There we have water and vegetable oil. If you mix together water and vegetable oil, very similar to what we saw when we mixed together the hexane and water here the other day, we saw that they would not dissolve, they would not mix with each other. Yes?
Is alcohol miscible or immiscible for vegetable oil?
Actually, alcohol will dissolve a small amount in vegetable oil. They're not completely miscible with each other.
So miscible and immiscible are the extremes, and there's this little middle that we don't really talk about.
Well, we do talk about it, and if there's somewhere in the middle, we call it partially miscible. So, and then if we were to talk about solubility, we might say it's partially soluble. So when it comes to miscibility, though, we do, yes, typically talk about the extremes, either that they can mix together in any proportion or they can't. Okay, good point. Then, if we look at our next terms, we go down, we have gaseous, liquid, and solid solution. Usually when we think of solutions, we think of something like this, something that is in a liquid state. But if we go back to our very first term here that we looked at on the Socratic app today, we're talking about a homogeneous mixture. And a homogeneous mixture does not mean that we have to have it confined to a liquid state. We could have it in a gaseous state, we could have it in a liquid state or a solid state. Yes, when?
The air would be a gaseous solution, right?
Exactly. So air would be an example of a gaseous solution. Air would be an example of a gaseous solution. Liquid solution, again, are the ones that we're most accustomed to. So when we talk about these solutions as their phases, this is what their final phases represent. And so again, air would be a gaseous solution. A salt solution, like I have here, would be an example of a liquid solution. How about a solid solution? Many of us actually have these in our mouths. If you have a dental amalgam, if you have a silver filling, the silver filling actually isn't silver. It's actually, well, there's actually a small amount of silver in there, but actually one of the primary components of a dental amalgam, which again is a filling, is mercury. Which, when people hear that, they think that's really kind of bizarre, because after all, what do we know about mercury? Very toxic. Okay, but if you have a silver filling in there, you actually have mercury in there. But the mercury stays trapped in there, and the mercury itself, and now there is some debate. Some will say that, you know, heck, I'm not going to have mercury in my mouth anymore, and they'll go and they'll have all their silver fillings popped out, and they'll replace them with some sort of composite filling, something that matches the color of their enamel. But mercury is a component of a dental amalgam. And when it comes to mercury, it's actually not the metallic mercury that is toxic to you, it's the ionic form. So mercury, either in its 1+ charge form or its 2+ form. The actual metal by itself is not toxic. So you might say, well, if it's the charge form that's toxic, how come there's such a concern about liquid mercury? Any idea whether there's a concern about liquid mercury? Even though by itself it's not toxic.
Because it can get absorbed in our skin.
It actually doesn't even absorb that well in our skin. What happens is that just like any liquid, water, if it sits out in an open container, if I open up, I don't have water here right now, but if I had a container of water sitting here, what happens to that container of water over time? It evaporates. And any liquid will evaporate. So even mercury, we don't think of it as being a liquid like water's liquid, but it's going to evaporate. And what happens then actually is those molecules of mercury will get out here, not the molecules, but individual atoms. And when we inhale those, then what will happen is that those individual atoms are very easily ionized. And so even though the metallic mercury itself is not so toxic, because it is so easily ionized, that's what makes it toxic. And so we'll inhale those vapors. And so that's the biggest thing. We used to have mercury barometers here, we used to have mercury thermometers, but then what would happen is if we broke a mercury thermometer, what happened is that the mercury, even if it's just this tiny little drop, could wind up in the cracks or whatever in the tile. They're not easy to see, and because it is a liquid, it could wind up easily evaporating. And so because it would evaporate, then we could wind up inhaling it, and then our bodies can easily change that atomic form into an ionic form. But in our mouths, that mercury is locked in its atomic form, and it's mixed in with several different substances. In fact, most metals that we're familiar with are not pure. This is not pure iron. This is iron with some chromium, some nickel, probably some carbon in there. You look at it though, it looks like one substance. So when we talk about metal alloys or coins in your pocket, those would be examples of solid solutions. They're not pure metals, they're a mixture of different elements. Any questions on those? All right, next up, we have the terms aqueous and non-aqueous solution. So if we have a solution in which water is the solvent, what do we call this? darn well better get this one. We'll count down. 5, 4, 3, 2, 1. That is an aqueous solution. This is an aqueous solution. Good. And then our next terms here are the terms dilute and concentrated. Dilute and concentrated. And these here are relative terms. And they pertain to the amount of solute that's dissolved in a solution. So if we have a solution that contains a relatively large amount of solute, remember that's the stuff that we dump in. That's the stuff that gets dissolved. If we have a relatively large amount, is that a dilute solution or is that a concentrated solution? We'll count down. 5, 4, 3, 2, 1. And that would be a concentrated solution. So think about that. When we talk about people are concentrated in the room, that means we're really close together. So a solution that has a relatively large amount of solute would be one that is concentrated. Now, the next three terms here are ones that I'm going to demonstrate, and we're actually going to provide some definitions for these. And we're going to start by looking at a definition for a saturated solution. Okay, so we're going to look at saturated. And for a saturated solution, we define a saturated solution something like this. We define it as one that contains the maximum amount of solute that will dissolve in a specified amount at a given temperature. And so just like when we talked about hydrocarbons, we talked about saturated hydrocarbons and unsaturated hydrocarbons. We say that something is saturated, that means it is full of something. And so what is a saturated solution full of? Solute. It's full of solute, that's right. So it means that we cannot hold any more solute in there. It's full of solute. And if we look at this definition a little further, we should notice that there are three different variables that are specified. One is the amount of solute, one is the amount of solvent, and the other is the temperature. So this is a three-variable definition, and we're going to talk about that here in just a moment. So again, a saturated solution contains the maximum amount of solute that will dissolve in a specified amount of solvent at a given temperature. Then we have an unsaturated solution. And an unsaturated solution we define like this. This is one that contains less dissolved solute than a saturated solution at the same temperature. And then if we go to the last one here, basically what I'm going to do is I'm going to copy and paste this definition right here. We'll copy this, and we'll come down here and we are going to paste this. And we're going to change this just slightly. And in the change, we're going to call this a supersaturated solution. And we only need to change one word in here. And what word would we change?
Less.
Less. And we change that to?
More.
More. Exactly. So an unsaturated solution is one that contains less dissolved solute than a saturated solution at the same temperature. And a supersaturated solution is one that contains more dissolved solute than a saturated solution at the same temperature. And so we're going to demo each one of these here so you can get an idea of how each one of them behaves. And I think we can get them all on the same screen. Here we go. And I'm going to demo these by using my webcam. And so I brought my webcam out here today. And hopefully you should be able to see what I'm demoing. And have some solutions. Here we go. Perfect. And you should be able to see what's in them. So these are each salt solutions. These are each salt solutions. And what I'm going to do is I'm going to go ahead and add some salt to each one of them and then shake them up and we'll observe what happens. And I'm actually going to turn these around so they are kind of in your, so you can look at them from left and right. So here's the one on your left, here's the one on your right. There we go. And we'll go ahead and put in kind of equal amounts, if we can, of salt into each one. And that's just kind of eyeballing it. And I'll keep them in the same order. We'll shake them up. And then we're going to see what happens to them. And then we should be able to come back here and take a closer look. Now the one here that's on your left, if you notice what's in the bottom here, notice we still have a bunch of salt in it. The one here that's on your right, notice that the salt did dissolve. So this one here, which the salt did not dissolve, what do you think we would have called this?
Supersaturated.
This was?
Oh, was.
Is or was? Let's start with was. Was this one saturated or unsaturated to begin with?
Saturated.
This was saturated. This one must have been? Unsaturated. This one was saturated because we said that a saturated solution was full of solute. It could not dissolve anymore. And then an unsaturated solution is one that could dissolve more, so it contained less than a saturated solution. So one of the tests then of whether a solution is saturated or unsaturated is simply to try to dissolve more of the solute into it. Now, if I were to pour this liquid off of here and save this, would this liquid portion, would this be saturated, unsaturated, or super saturated? Well, it is still going to be saturated because if we say that it contains the maximum amount of solute that will dissolve at a given temperature, and we try dissolving more in there, that means that the solution is still going to be a saturated solution. We can't put any more in there, it's still going to be saturated. And again, the key there is we talk about it being a dissolved solute. So we come back to our definitions here. We say that it contains less dissolved solute than a saturated solution. This one here is more dissolved solute than a saturated solution. And here we talk about the amount that will dissolve. So this solute that's in here at the bottom is not dissolved. And so the fact that we were not able to dissolve anymore tells us that this solution is still a saturated solution. So what I have brought out here then is a couple solutions that are supersaturated. And these solutions are supersaturated with sodium acetate. I'm going to put this up a little closer here so you can see how this appears. And this one now, again, is a supersaturated sodium acetate solution. So the stuff that's in there is sodium acetate. And what I'm going to do is I'm going to go ahead and try dissolving some more sodium acetate into the solution. And to do that, I need to clean off my spatula. I want to make sure that it's nice and clean. And then what I'm going to do is I'm going to add in some sodium acetate, but I want you to see how much I'm going to be adding. It's kind of hard for me to control this, because what I'm trying to do is I'm trying to get this much on the tip of the spatula. And I don't know if you can even see that. I don't think we can. But what I'm trying to do is I'm trying to add in 1 drop of the solute. So we have a liquid solution. I'm going to drop in the 1 crystal of sodium acetate. And notice now what happens when we do that.
That's a lot of
Okay. So we'll give it another shot. Except this time now, this here is a sodium acetate solution. And instead of putting in some sodium acetate into this one, again, this is a supersaturated sodium acetate solution. But into this one, instead of putting in some sodium acetate, I'm going to try adding some salt. So watch what happens when I try adding some salt to this supersaturated solution. And if you're noticing nothing happens, you are correct. You might see the crystals there kind of floating on the top, and they're kind of sitting right up here yet. So what I'm going to do is I'm going to come back to here, and before I actually add in the sodium acetate this time, I need a couple of thermometers. So just someone here to grab the bottom, just feel room temp. Room temp. Okay. All right. So what I'm going to do with this one now is I'm going to go ahead and take 1 crystal of the sodium acetate again, and now there I have 2, now I'm down to 1. And now this crystal is just a little speck, just like the salt is. And we'll go ahead and add this 1 little speck. Again, you can see how the solution is mixing there. Drop in the 1 crystal. So, your next question on your Socrative app is this. When the solute in a supersaturated sodium acetate solution crystallizes, predict. Do you think that the temperature increased, decreased, or stayed the same? And we saw that they were at room temperature, and I'm going to go ahead and, if you have your answer locked in, lock it in. Okay, and then pass this around and feel it, pass it back, and see what you observe. Okay, let's get it to the back. And then we'll check out our predictions. All right, we'll check this out here. And we see as a class, most of us predicted that the temperature would decrease. But actually, what's happened to the temp? It went up. Okay, now, can you think of a use for this?
Heat packs?
Yeah, heat packs. Heat packs would be an excellent use for these. In fact, that's exactly what I brought in here. I brought in some heat packs. And what I'm going to do here is bring these around and give one to you. Just hold on to it, don't play with it yet. Give one to you here. And Connor. We got one there. Let's go with this one. Grab one. So now, these are some portable heat packs. And these portable heat packs are made up of supersaturated sodium acetate. And in the center of these, if I grab one for just a moment, I'll give it back to you. In the middle of these, you're going to see that there's a little button. And I'll show this button right up close here. There's a little metal button that sits inside of here. And what we're going to ask your peers to do is you're going to kind of click on that button and kind of press on it, but don't do it quite yet. You want to make sure that everybody can see. You're going to click on that button. Once you click on that button, then you can go ahead and hold it up for everybody to look at around you, and then watch what happens when you do it. So go ahead and click on that button. And then once you click on it, you need to press on it. Just pinch it or whatever. You'll hear it click. And then watch what happens to it once you do. Just press on it. There you hear it click? Yep, there you go. Hold it up so that people can see what's happening. And then you can go ahead and pass it around so everybody can feel how that feels. And now I'm down to like 4 packets. I had 10 of them here about 3 or 4 years ago. But this here is one of the applications of what we just saw. That packet there is a supersaturated solution of sodium acetate. And one of the nice things about it is it provides instant heat. And any of you ever used those before? And what's one of the ways you use them? Or when do you use them? You say you use them. So when have you used them? Winter? Skiing, heating, ice fishing, hunting, football games? Sure. So they all work very well. And one of the nice things about them is that they provide an instant source of heat. And this afternoon now, one of my colleagues is going to use these very things. And when they use them, how do you suppose I can reuse these? Throw them into some hot water. If I throw them in hot water, what will happen is that I can redissolve these and use them again. Yeah.
My sister bought some from Mall America, and the ones she got, she could freeze them, and then they could use them as like ice packs, and then she could boil them and use it.
Yeah, very cool. Yeah, and it's probably the same thing. And one of the reasons why it works well as an ice pack. Let's see. I'm trying to think here what we've gone through thus far. You might remember when we did the lab with the snow. Actually, we had ice in there, and we added some salt to it. What happened to the temperature when we added the salt to the ice and water mixture? The temperature went down. And so one of the reasons why it can be used as an ice pack is because it winds up lowering the freezing point. And so because it lowers that freezing point, it makes it much, much colder, makes them wonderful ice packs as well. So yeah, they work very well for that. So now this afternoon, well, what I'm going to do here right after class is I'm going to go ahead and throw these into a pot of boiling water. We'll heat them up, they'll redissolve. Of course, I can't leave them hot. Then what I'll need to do is cool them back down to room temperature, and then I can reuse them. Same with these. These will also be reused this afternoon. And how will we be able to reuse these? We're going to place them onto a hot plate. We'll get them to redissolve. Once they're redissolved, we cool them back down to room temperature, and then they can be used again. And so that's the way, if you're wondering, how in the world can we have this supersaturated solution, one that contains more solute than a saturated solution, when after all we said that a saturated solution contains the maximum amount. And the way that we do it is by remembering that this is a 3-variable system. And the third variable here is the temperature. So we can heat these up, get them heated up to the point so it's actually unsaturated at a higher temperature, and then cool them back down. And supersaturated solutions have a number of different uses. And you've actually seen them before. Any of you ever made rock candy before? Okay, rock candy is done making a supersaturated solution. And if you made rock candy, what you make is a supersaturated solution of sugar. Okay, so you go ahead and you take out your pan, you dump in some water, and then you dump in a whole bunch of sugar in there, heat it up until the sugar winds up dissolving, then you cool the sugar solution back down to room temperature and suspend a string inside of there. And then what will happen is that the crystals of sugar will begin growing on that string as the water evaporates. And so it doesn't come out quite as fast as this does here, but it does come out nonetheless. Have you ever had honey before? What happens to honey if it sits on the shelf? It crystallizes. And it crystallizes because honey is a supersaturated fructose solution. And of course, nobody likes to put, granular honey on their bread. So if you don't like the granular honey, what do you do with it? Yeah, you can put it in a pan of hot water or put it in the microwave, get it to mix up, redissolve that sugar, and you can use it again. And usually what happens to the honey is it will sit there for a while, and all of a sudden something will trigger it, just like this here. Something will trigger it and will cause that crystallization to occur. And then it kind of goes back and saying, well, how come it was then when I tried taking the salt and putting it in here, the salt did not cause this to crystallize? Yeah.
Because it's a different solute.
It's a different solute. Remember that this was supersaturated with sodium acetate, and this stuff here is sodium, what is this stuff? Sodium chloride. So it was supersaturated with a different stuff, so when I tried putting in the sodium chloride, that did not cause the crystallization to occur. And what I'm looking for here, I have a magnifying glass, and I'm going to pass around something for you to look at. Here, maybe I'll take this out. And need to clean this out just a bit. And part of it has to do with the crystal structure, whatever it is we're looking at. And so what I'm going to do is I'm going to place some salt into this beaker, and we will put the magnifying glass into there. And if you pass this around and take a look again, you can take it all the way to the back and pass it forward. What you're going to see is that all of these salt crystals have the same shape. They all have a cubic shape. Something like sodium acetate probably isn't cubic. It probably has something different than does the sodium chloride. And so it has to have the same crystal structure in order to build up in 3 dimensions. And by placing a seed crystal, that is simply by taking one crystal like I did here and dropping it in, that one crystal has the right instructions, it has the right buildup, so that all of the crystals can build up in 3 dimensions off of that one seed crystal. So anyhow, that's some stuff on here. As far as the other hand warmers go, many of you, probably more of you, use this type here. And this type here, and I have some pictures, larger ones here. You've probably noticed them, they have the cloth bag, and they're contained in an airtight container. And if you pass these around and look at them, and let's see here, it lists the contents in here. You'll notice the contents are iron powder, water, and so forth. These operate a tad bit differently. And let's talk about hand warmers since we have the weather appropriate for it right now. Again, we have 2 types of hand warmers. We have the one type, which is the supersaturated. Sodium acetate solution that we just passed around. And we have the other one that's going around here, and this one here is one that consists of iron powder, and then you'll also see it contains some salt and some water. That's kind of the three top ingredients that are in there. And then there's also some charcoal that's listed as well. And the charcoal actually prevents the odor from being too strong. But we know this in Minnesota. Our cars are made up of which element primarily? They're made up out of iron. And when they're exposed to salt, what happens to them? They rust. And what happens actually is a very simple reaction. The process of rusting is iron reacting with oxygen to produce iron oxide. And the oxide that's produced is actually iron-3 oxide. But this is here what actually happens in the process of rusting. It's basically iron reacting with oxygen to produce iron-3 oxide. And of course, if we balance the equation, it looks like this. But what happens then is that when you tear open that package, the one that's going around right now, the little hotties, when you tear that open, it exposes the contents to
Oxygen.
the oxygen in the air. And that's why we have the cloth bags. So this one here, we had a plastic bag. We want to retain the contents in here. But in these here are made up of the cloth bags because they allow the oxygen to pass through there. And you might remember when we talked about combustion, this is really a combustion reaction. Whenever we react oxygen with a substance, and combustion reactions are always reactions that are exothermic. That is, they give off heat energy. So when these two combine with each other, they actually give off heat. When your car is rusting, it is actually giving off heat. We don't feel it because it happens over such a long period of time. But if we took that car and ground it up into a powder, like we have here, that will increase the surface area, increase the surface that is available to react, and that will cause that reaction to speed up. And the whole purpose of having salt in there, well, the salt, just like the salt on the roads, salt is a catalyst for this reaction. So if we add in the salt, add in a little bit of water into those packets, then that will cause that reaction to speed up, and it will give off heat. And those there, if you want to reuse those, you actually can't reuse those hot packs. You can't extend their life. You know how we can extend the life of those hand warmers? Well, one reactant is oxygen, so we need to basically cut off the source of oxygen. So we can put it into a bag. If we put it into an airtight bag, we can go ahead and stop that reaction, and then we can open up that bag again and cause that reaction to go. So they, once we use up, however, all of the iron powder in there, we can't take the reaction backwards, and those then are not reusable. Those are ones there that once they're used, we toss them out and we need a new one. The advantage of these, of course, is that these here are reusable. And you can see as we pass them around that these are looking kind of worn out. We've used these quite a few times here over the years. Started, I think, with about 10 of them. We're down to 4, and so we're ordering a few more right now. But this reaction is also kind of a fun one. And this is actually not a reaction, and this is a physical process. But we're going to be using these this afternoon, and again, in order to reuse them, we need to do what?
Heat them and then cool them back.
We need to heat them up to get them to dissolve and then cool them back down to room temp. So I have quite a history with these, and here's one of those things that happened to me some years back. In my first year of teaching, I was teaching down in the town of Waseca. I was teaching high school, and these here will sit for a nice long time. I usually put a beaker, inverted beaker over the top to prevent the water from evaporating, and so I can set these away, and then when I'm ready to do them, again, just heat them up, get them to dissolve, cool them back to room temperature. So while I was teaching down there, we had one of these things called a snow day, And I had these class that were sitting around and said, oh, you know what, today would be a great day to redissolve my sodium acetate solutions. So what I did was I put them onto a hot plate and turned up the heat. One of my buddies came by and said, hey Lance, how do you like to go to lunch? I said, sure. So we went off to lunch and came back from lunch about an hour later, and the hallways just reeked of vinegar. Now, why would they reek of vinegar? Remember, the stuff that's in here is sodium acetate. The acid found in vinegar is acetic acid. So it's the same ion that's in there. And so right away I was like, oh no, what happened? And I walked into the classroom, and they were sitting in the classroom because I was the only one that had that classroom, and these things had been bumping and spraying. And if you look at this, the way this is designed, this is like the barrel of a shotgun. Okay? So what happens is that these solutions are very viscous. If you can imagine like heating honey or whatever, or gravy on a stove, what happens to it if you heat honey or gravy? A real thick. It spatters, and of course this is spattering, like just like a barrel or shotgun, and it was shooting it up onto the ceiling. And what happened was it was actually sitting underneath one of these vents like this. So, of course I walked in there and I said, oh crap, you know, what am I going to do now? So I go ahead and I wipe up the entire mess. Well, the next day I come into class and I see these little droplets of water sitting around. I couldn't figure out what was happening, so I wiped up these droplets. Then all of a sudden there was these white smears all around. Okay, so I take some water, wipe it down again, day is all right, and then next day I come in and there's all these little droplets sitting there. And what I figured out had happened is that shot a whole bunch of that sodium acetate up into the vents. Every morning when the heat kicked on, it caused these flakes to come down out of the vents. Those flakes would land on the table, and sodium acetate is a hygroscopic substance, which means it absorbs moisture from the air. And so every time these flakes would come down, they'd be the white flakes that absorb the moisture from the air. I would do a crappy job cleaning it up, and there's these white smear marks. And it'd take me like about 3, 4, or 5 minutes every day to kind of wipe up this mess. And this went on for about 3 months. You know, this whole thing would come down. So, next year, we had another snow day. I made up some new solutions, and snow day came, and it's like, oh, this would be a great day to redissolve my sodium acetate solutions. I'm not going to get fooled again, right? So I put the hot plate in my office, put them onto the hot plate. My buddy comes by and said, hey Lance, how'd you like to go to lunch? Sure. They take off for lunch. I come back an hour later, the hallway's just reeked of sodium acetate or vinegar. So I go into my office, and there's this sodium acetate sprayed all over the walls and ceilings in my office, and had to clean that up. And so for years and years and years I've been telling this story, and probably about 10 years ago, now I have a lot more students. Then there I only had, well, I had 200 students, so my classes were small. Here we go back to back to back to back, and I don't have a chance to redissolve these things. So we have a whole bunch of these. I have more lined up over here. So after class I had like 4 of these things, and we have a big hot plate sitting in our prep area. Set them all on the hot plate. You know, exam 4 is coming up, right, and everything. Go into my office, and pretty soon our lab manager comes running out. What's going on in the prep room? And so I have 4 of these things shooting off like shotguns into the walls in there. And so now I'm not allowed to touch these things. I tell the story, somebody else does the redissolving because I can't attend to these. But anyhow, so with this, we have one more term here, I think, if we go back to our list of terms, and that is solubility. And if we look at the definition of solubility, we define solubility like this. And it's going to sound very similar to that of a saturated solution. We define the solubility as being the maximum amount of solute that may dissolve in a specified amount of solvent at a given temperature. So really about the only difference between solubility and a saturated solution is that a saturated solution is the solution, and it is the solution that represents the solubility of a substance. So in here, in this definition, we specify three quantities: the amount of solute, we define the amount of solvent, and we define the temperature. And this is what the solubilities look like. This here is what we call solubility table. This here represents a solubility table, or solubility curves. And represents the solubility of several different substances. And if we look at the axes here, I'll kind of blow this up a bit. On the vertical axis, the y-axis, here we show the grams of solute. And we see that this is the grams of solute per 100 grams of water. And down here on the x-axis, we have the temperature. And so when we want to talk about the solubility of a substance, what we really need to do is we specify all three variables. So for example, let's say we want to talk about the solubility of potassium nitrate. If we want to talk about the solubility of potassium nitrate, let's say we want to talk about its solubility at 20 degrees Celsius. So we follow this curve down here. At 20 degrees Celsius, it looks like we're at about this point right here. So then what we'd say is this. We could say that the solubility of KNO3 is, and then we would go ahead and interpret from the graph those values. So we come over here, and it looks like that value is somewhere right around here, somewhere right around maybe 32 or 33. And so we'd say then it contains 32 grams of KNO3 per, so it's 32 grams of KNO3 per 100 grams of water. This specifies only two variables, so we still have yet to specify the third, which is the temperature, which would be 20 degrees Celsius. So again, in the solubility, we specify these three amounts. So with that in mind, I believe I have three questions here for the solubilities, and I'm going to, and these are on the Socrative app. So I know that might have bumped you off, so we'll go ahead and give you a chance to get logged back in. So we're going to examine the solubility curves, and we'll look very carefully again at the solubility curves. We'll put them back up here. Notice now that there's two different types. We have the solids, which are the solid lines. We have the gases, which are the dotted lines. So from your vantage point, look at the solids, which are the solid lines, and answer the first question, which says, examine the solubility curves. When the temperature increases, the solubility of solids tends to do what? So as the temperature increases, here's the temperature. As the temperature increases, what happens to the solubility of solids? So we'll get our answers locked in, and we'll count down. 5, 4, 3, 2, 1. They increase. Very good. Next, this is with gases. When the temperature increases, the solubility of gases tends to do what? And look at them carefully. And we'll count down. 5, 4, 3, 2, 1. They tend to decrease. So again, if you look at these here, you'll see that this one will decrease in solubility, decrease, decrease in here. And then finally, the last one here, and actually I think it's our second to the last question. The solubility of KNO3 is blank grams, so just enter a number only per 100 grams of water at 70 degrees Celsius. So here's our KNO3, and I will relabel the temperatures here so you can see them. This is 10, 30, 50, 70, 90, so again, enter in a value. We'd like to know the solubility is how many grams of KNO3 per 100 grams of water at 70 degrees Celsius. So get your answers locked in, and we'll count down. 5, 4, 5, 4, 3, 2, 1. And looks like we should be right around 140, 139, 138, thereabouts. And we get that one by looking at 70 degrees Celsius. Looks like it's right about here. There we go. Just a hair below 140. So then if we come back here, if we want to write that out, what we'd say is the solubility of KNO3 is 139 grams of KNO3 per 100 grams of water at a temperature of 70 degrees Celsius. So again, with solubilities, we need to specify all three variables when the solubilities are given. Now, a couple of things that we'd like to point out here. First of all, this whole difference between solids and liquids. In other words, why should solids increase their solubility with an increase in temperature? Why should gases decrease their solubility? And this one here is very easily explained. First of all, what happens to molecular motion when we increase the temperature? Things move faster, right? The speed increases. So if we increase the temperature, molecules should move faster. So if we're dissolving something, if we heat it up to a higher temperature, the way that a solid can be more mobile is to actually dissolve. If it stays solid, they're really confined and constricted, and so by putting them in aqueous phase, that makes them more mobile and makes them more likely to dissolve. Whereas for gases, notice now that their solubilities decrease with an increase in temperature. So if a gas is dissolved in a liquid, how do gases become more mobile?
Staying, I guess.
They stay as a gas, so they would then be more likely to want to escape and go into the gaseous phase. And so by heating it up then, we're more likely to drive off those gases. And so one of the things that we could look at then might actually be a diagram for dissolved oxygen. If we looked at dissolved oxygen and we looked at a graph that plotted solubility versus temperature, what we'd see for dissolved oxygen is a graph that looks something like this, where this sits here at 0 degrees Celsius, and the maximum solubility sits right at a temperature of 0 degrees Celsius. And so we kind of got cut off on this in our last class period, but we talked about why do scientists look for water as a sign of life. And we said, well, one of the unique characteristics of water is that it had a relatively high boiling point for a very low mass molecule, and that made it very unique. But one of the other unique characteristics of water is that its density as a solid is actually less than its density as a liquid. And so its density as a solid is less than its density as a liquid. What happens to ice?
Floats.
It floats, exactly. Ice floats on the water. And so that's another thing that makes life possible here on the Earth, is the fact that ice floats. You might say, well, how does that make life possible? Well, think about Minnesota. If ice was actually more dense than the water, the liquid water, what would happen to the ice when it forms?
It would form at the top and then it would sink.
Sink to the bottom. It would form on the top and sink to the bottom. And it would keep forming on the top, sink to the bottom. Eventually those lakes would wind up
Frozen.
becoming totally frozen, totally solid. And the fact that water actually has a density that is less as a solid than as a liquid makes life possible, because that keeps the life in that aqueous form viable. But here's yet another reason why life can survive. As our lakes are going to begin freezing over here in the next week or so, turns out that the maximum solubility of oxygen is right at 0 degrees Celsius, which is the temperature at which water freezes. So as the ice forms then, it's actually going to have as much oxygen in it as it could possibly have locked in there throughout the winter. And of course, you'll still have a few plants that remain in the water that will wind up photosynthesizing and generating oxygen. But for the most part, it's going to lock in that oxygen, and it's going to be at the highest solubility that it can have. So a couple things is done to kind of combat some issues we have. One of the things that you probably haven't heard of is something called thermal pollution. And usually when you think of pollution, you're thinking of pollution with chemicals and such. You're thinking about toxic substances. Thermal pollution is an issue. And one of the reasons why it's an issue is if you think about how many of our aquatic species survive, like fish, for example. Fish survive based on oxygen that is dissolved in the water, and they absorb that oxygen through their gills. Okay? And if we have the water that's too warm, what happens is that causes the oxygen content to go down. If it goes down, they cannot get enough oxygen absorbed through their gills because there's just not enough oxygen in the water. And the consequence of that is thermal pollution. Now, I'm not a large, I don't fish a whole lot, but any of you fish for trout or stuff like that? Anybody fish for trout? Anybody know what type of habitat trout survive in? Very cold water. Okay, so they are typically found in spring-fed creeks and rivers. And we'll find them in things like Lake Superior, which is very cold, but we're not going to find trout out here in the Mississippi River, because the Mississippi River is a warm river, relatively speaking. But if you go to a spring-fed creek, there's a good chance you'll find trout surviving there. Well, you might wonder now, why do we'll see road construction or whatever, and you'll see that they'll build up these big gates or fences there to prevent runoff into those creeks. Well, part of it is to keep the creeks and everything clear of silt and dirt and stuff like that. But another reason is that water that runs off of highways and such can cause those creeks to warm up in temperature, and as the temperature goes up, that can cause the survivability of aquatic species to go down. The same thing happens when we design sewer systems. For example, we have storm sewers here. Anybody know where the storm sewers empty out ultimately in Coon Rapids?
Mississippi.
Right, they go out here into the Mississippi River. The water comes down, you see the grates out in the roads. There's some big pipes and culverts there, and those pipes eventually lead out to the Mississippi River. So what can happen then is that in the summers when we have thunderstorms, thunderstorms typically follow what kind of weather? Really, really hot weather, really humid weather, and that water will fall down onto those hot sidewalks and hot pavement, and then we'll go down to those storm sewers. That water is going to be very warm, and that water is going to wind up running out into the river, and that will cause the temperature to go up, and of course the solubility of the oxygen to go down. So we find ways to try to combat that, and one of the things that was done, I worked at an electric power plant when I was living down in Iowa, and the power plant kind of sat up here. This was down in Sioux City, Iowa, and then sitting down below here was the Missouri River. So the river sat down here, the power plant sat up above. Now, if you've ever driven by like the power plant up by Big Lake in Monticello, you'll see that it gives off tremendous amounts of heat, and that's because the heat the water is used to cool down the turbines and such in the power plant. And that water at the power plant ultimately goes back into the river. So what is done though at the power plant, and this is what was done at the power plant that I worked at, coming outside of the power plant was something that looked like this. And it was kind of these cascades here. And so as the power plant got rid of their water, that water would run down these cascades. And the whole idea of running down these cascades was to do two things. One of them was cool off the water. If you can churn up the water, that's going to cool things down. What is the other thing it's going to do?
Oxygenate.
It'll oxygenate it, it'll aerate it. Because as it bubbles down, it causes it to mix with the oxygen in the air. And so by cooling it down and mixing with the oxygen in the air, we're at least trying to get that solubility back up here to increase the survivability of aquatic species and such. So
One up by Big Lake apparently does a good enough job because the swans can survive there, and if they can survive there, then so can the plants and the fish.
right. Have any of you ever been up to see the swans up on Big Lake in Monticello in the winter? Yeah, so the Mississippi, the power plant there keeps the water actually open all winter, but they're able to survive mainly because of the survivability of the various types of aquatic species that are in there. Okay, so that's kind of our introduction to solutions and solubility. On Thursday in here, there's one more question waiting for you in the Socrative app. On Thursday, we are going to be going into concentration calculations. And when we start talking about concentrations, we are going to use some different units to represent those concentrations. And so now, before you start answering this one, there are several correct answers on here. So let's just talk very quickly about what concentration is as far as a unit. If we talk about how concentrated something is, we want to talk about how concentrated a solute is per unit of solution or per unit of solvent. So think about the units here, one that would represent how concentrated solute particles might be. And there's going to be several correct answers. Go and select all of the correct answers that apply. And then I have one demo to wrap things up here today. I think I might have it out here. I do. Now, in order to do this demo, I need to borrow some money from someone, because honestly, I could show you my wallet, and I am totally broke right now, other than my credit cards.
Will we get the money back?
I get the money back, and I want to see who has the largest bill. As long as you promise not to bump that person off after class.
20.
Who's got the biggest bill? Anybody have a 20? Or what do you have?
I have a 20.
Anybody have 100? Do you? Oh, guys, I haven't done this with a $100 bill for how long? It's fun. We'll get it back. How about that? Thank you. Now, I actually don't know if it works with the new $100 bills. We'll find out. I'm good for it. It's recorded, so we'll find out if it works or not. So this is the first time actually with the new hundreds. But let's check our answers here really quick to see how we did. And where's my stylus? I'm always losing it. Here we go. So, all the ones here in green are correct. Again, concentration is anything which shows an amount of solute per amount of solvent. So this would be milligrams per deciliter, parts per million, parts per billion. Proof, molarity, which is something we'll get into, percents. Proof is one though. Anybody know where proof comes from? Alcohol, exactly. And I've actually just made up a solution here. This is a mixture of the rubbing alcohol and some water. And if I made this up correctly, this is about a 50-50 mixture of alcohol and water. And what I'm going to do here now is I'm going to go ahead and turn on this burner. There we go. And we're going to turn these lights down a little bit. You don't need it down a whole bunch. But I'm going to go ahead and take this bill and I'm going to dip it into here. Anybody know where the term proof comes from? Anybody know what the word proof, let's see, what proof stands for when it comes to alcohol? If something is 100 proof, it is about 50% alcohol. Proof is equal to the percentage times how much? Times 2. So 100 proof is 50% alcohol. So what I'm going to do here, let's go ahead and dip it in again. I've talked a little too much. And dip it in again, like this. There we go. We'll bring this over here.
I'm still on fire.
Yeah, and you see that it stopped. I can go ahead and do this again. And we'll go ahead and take the bill. And any idea why the bill does not burn completely?
Because
Right, the alcohol is flammable, but the water is not. And where the term proof came from, thank you, by the way, Alex. Where the term proof came from actually comes from the days of the bootleggers. It'll dry out. It comes from the days of the bootleggers. And of course, the bootleggers are the ones that made illegal alcohol, illegal whiskey and such. Well, if you're one selling an illegal product, one way, especially like alcohol, one way to make more money is to water it down, right? Okay, but if you're the one buying it, what do you not want?
it watered.
You don't want it watered down. Okay, so what was done then is that in the days of the bootleggers, you'd go ahead and put some gunpowder down, and then you'd pour the bootleg or the alcohol over the top, and you'd take and ignite it, and what would happen is that the alcohol would wind up burning off. And if the gunpowder also ignited, then it was proof that it contained a certain amount of alcohol, and that certain amount was about 50%. And so if there was too much water in there, what would happen is the alcohol would burn off, the water would go ahead and keep the gunpowder wet, and the gunpowder would not ignite. And so again, that is somewhere around 50%, which is 100 proof or 100% proof that it contained a certain amount of alcohol. And that's kind of a history lesson there. So Have a good one. Happy Thanksgiving to all of you.
You too.
Celebrate well. Come back healthy. Be safe on the roads today.